Alright, and here we are again. This will be the last video in our pure parallel RL circuit with single components in each branch. And in this one, we're just going to do a review with just the arrows, no numbers. Very similar to what we did in our series RL circuit. Okay, so first we're going to start by varying frequency. So in this one, frequency is going to go down. So when frequency goes down, we know that frequency affects the ohmic values of our two inductors. So we are expecting those ohmic values to decrease. Remember, it is just a multiplication problem. So you put a smaller number in, you get a smaller number out. So both the inductive reactance for L1 and the inductive reactance for L2 we're expecting to go down. Alright, now that combined ohmic value, right, is going to be smaller than the smallest value. If both of them are going down, we would expect that combined value to go down as well. Now, again, reciprocal formula, if you've got one of those that are continuing to go down, right, you're going to see that total also go down. It's going to be smaller than that smallest number. So if your numbers are going down, you're going to see a smaller total. Alright, so if the total ohmic value for the circuit impedance is going down, we're expecting total current to go up, and it does indeed. Now the current through your resistor, remember that one is not going to change, and that is because voltage stays the same and resistance stays the same. With both of those the same, it's impossible to get another value. It's impossible for it to go up or down. One of those would have to change. And so our current through our resistor, or the current through branch 1 in this case, would stay the same. Now, the current through branch 2 and branch 3, however, is going to do the opposite of those ohmic values in branch 2 and branch 3. And we know that our inductors' ohmic values are going down. So if those ohmic values in branch 2 and branch 3 are going down, the currents in branch 2 and branch 3 are going up. And that is how you work it with just the logic behind how it works. Alright, let's try it again, but let's do frequency going up. So here we go. Exactly the same scenario, except in this case, frequency is going to go up. Again, the formulas for L1 or XL1 and XL2, or the inductive reactance of your inductors, is a multiplication formula. You put a bigger number in, you get a bigger number out. So in this case, we're expecting that ohmic value of L1 and L2 to go up. Now, the total ohmic value is a combined value of, or for our total inductive reactance, it's a combined value of L1 and L2. Now that is reciprocated, but if those numbers are both going up, we are expecting that value that is less than the smallest one to also be going up. Now again, that same formula that we've been looking at for the impedance, it too has a value that is slightly less than that smallest number. Well, if you have one of those values that is increasing, then that smallest is actually increasing, right? So we see that total ohmic value following the inductive reactance total, because resistance is not changing. And so in a mathematical formula, where you see a component that is going up, your, in this case for this formula, your total is going to follow that and also increase. Okay. So if impedance, or the total ohmic value of the circuit, is going up, then we would expect current to be going down, right? They are inversely proportional. Now again, just like we talked in the previous one, with the same voltage and resistance that is not affected by frequency changes, right? In branch 1 through the resistor, we are expecting to see no change in current. Remember, in order to get a change, you've got to have either resistance change or voltage change. Neither one of those are changing. So the current through branch 1 is the same. Now the current through branch 2 and branch 3 are going to do the opposite of the ohmic value in branch 2 and branch 3. And since those ohmic values are increasing, those currents are decreasing, which is another good way to look at the arrow logic. Sometimes it's a little harder to visualize arrow logic from the ohmic value side in a parallel circuit. So sometimes it's a little easier to look at current, because current is essentially a multiplication problem, right? It's the square root of the square. So when you look at total current, you have one current that stays the same and two of them that are decreasing. So with both of these currents decreasing, you're going to have a much smaller number when you combine those two currents, which is just adding them together. Now, with one current that stays the same and a combined current that is actually going down, you are going to have in your essential multiplication formula there a total current that is going down. And so if your total current is going down, of course your total ohmic value must be going up. So that's another way to kind of think about it if you're having a tough time with visualizing it through the total ohmic value route. Alright, and there is arrow logic. Just real quick, I didn't really go over it in the previous slide, but of course changes in frequency don't change any of the voltage. All of these branches have only one component, and with only one component, of course they are going to drop the entirety of the applied voltage on each of those components. So as we know from all of the parallel circuits we've seen, voltage is consistent or constant in this parallel circuit. So every one of those branches has 12 volts applied. Since there's only one component in each branch, each component has a voltage of 12 volts. Alright, and that concludes our parallel RL circuits for now. Like I said, I'll see about putting together one with some multi-components so we can look at some fault changes with multi-components.